I can continue the discussion a little bit further about the polynomials and their roots, and that's actually something which is a part of the question 17 in the yellow book. Well, in question 17, it's a little bit simpler question in comparison to what I'm going to just present right now, but the idea both in question 17 and here is totally identical. So the question goes like this. Imagine you have a polynomial of degree n. Imagine you have a polynomial of degree n, and you know that your polynomial this time, unlike the general polynomial, this time this polynomial has only real coefficients, like this. Question 17 and my lemma, it asks us to prove that if you have a solution, you do have a solution, that's the conclusion of the fundamental theorem of algebra. If you have a solution to your polynomial, then, and that's something we have to prove, the complex conjugate number of this solution will also be a solution. So for the polynomials with real coefficients, solutions always come with complex conjugate pairs. Something probably you observed quite often when you were solving quadratic equations. When you solve a quadratic equation, you end up with the complex roots. They always come with a pair, plus and minus I. This is a fact you observed numerously. Now we're going to confirm it with a logical proof. And we're going to confirm it in case of polynomial of any degree, rather than just second degree. Question 17, by the way, just speaks about the second degree alone. It doesn't give you the question in any degree, but the difference is, there's no any difference in fact. Yes. So when I said that the complex roots, they come with the complex conjugate pairs, of course I mean when you have a pure complex root, so the root which has non-zero imaginary part. If you have a zero imaginary part, then it's no longer true. They no longer come with it because you no longer have a separate complex conjugate. Look at the proof. The proof, in fact, is simple, but it's a good demonstration of the way you can present proofs sometimes. So we start with the assumption that my z is a solution, isn't it? That's something which is given to us. We have to establish this implication. That's why I put it under the question mark. We start with this assumption. The first thing I do, I just put this z across my expression for the polynomial. Here it is. I just sub in my z into my polynomial. The nth term, and take one term. Well, dots hiding most of the terms. The one before the last one, and the last one. And we know this is 0. Now, the main trick in this proof is this. I can take this identity now, or the main trick in question 17 as well. I can take this identity now, and I can apply complex conjugate to the whole left-hand side and to the whole right-hand side. Just put a long bar here, and a long bar, well, short bar, sorry, here. I'm not going to put this in writing. It will look horrible. I don't like horrible writings. But I just ask you to imagine this in your head. If I did that, and if I use the properties of the complex conjugation, one of them is if you apply a complex conjugate to a sum, this is identical to applying them individually. First term, second term, third term, fourth term, all of the terms. So if I put this long bar, and if I use this extra property, I can lower this bar over each of these terms individually. Now, if I use another property of the complex conjugation, that the complex conjugation of a product of two complex numbers, I can lower this complex conjugation to each of the factors individually. So I can keep lowering my bar even lower on A0 alone, on Z alone, A1 alone, on Z alone. All across my terms, I can do this trick, and that's something I'll put in writing. Here it is. Is the result of this double lowering of my bar on the left-hand side, on each of the terms and on each of the factors. Is the result of that. Again, dots hiding most of them, but the rule is, I think it's clear. Here's the left-hand side. Well, the right-hand side, there's nothing to do with the right-hand side. I mean, if you put the bar over 0, complex conjugate of 0 is just 0. So, well, actually, I put my bar over 0 here. Now, here comes the place where we're going to use this assumption, because This assumption is essential for the proof, isn't it? Because if you don't have this assumption, this is no longer true. if you have a polynomial equation with not necessarily real coefficients, it doesn't mean the solutions will come in complex conjugate pairs. So here's a place where we're going to use this assumption significantly, because complex conjugation of the A0 coefficient is A0. Complex conjugation of A1 coefficient is A1. All of the coefficients after complex conjugation, they remain themselves. Here's what I just said. So if I take this across my equation, if I replace each coefficient here with A0, A1 in AN, then the left-hand side, this is simply my polynomial again, but this time I plugged in z bar in this polynomial. So we conclude that the complex conjugate to the number z is also solution. Remember, this assumption was significantly used in the proof. Here's the place. If you present your own proof on any other statements you will ever prove, you have to make this also clear where the assumptions are used, because that's the content of the proof. Not the writings, but the places where the assumptions are used. Essentially, you have to make them very clear for the reader. And here's the example. It says here lemma is proved. Now, this lemma, it has another interesting consequence from the practical purposes of view, from the practical purposes. Imagine we're looking at the polynomial of degree 3 with real coefficients, right? Lemma says for such coefficient, for such polynomial, roots will always come with a complex conjugate pair, right? That's a clear conclusion. Well, but if every root comes with a complex conjugate pair, we will have even number of roots. Whereas if you look at the polynomial of degree 3, you at most will have, actually you will have exactly 3 roots. Whereas how we can reconcile these two apparently contradicting conclusions?
Some roots are real.
Some roots are real. And that's a very important conclusion. So not only via the fundamental theorem of algebra, we see that every polynomial will have a complex root in case of polynomials of odd degrees with real coefficients, we can always hope to find a real solution. That's another support for this informal way of guessing the solution. It must be a divisor of the last coefficient, a real one. So here's a corollary, which I put in writing here. If every coefficient is real and degree of my polynomial is, that's an abbreviation for the degree of polynomial. Degree of polynomial is odd number, then we will always have real solution. This exclamation point just emphasizes that the solution is real. It doesn't carry any other meaning beside the fact that I was trying to, emphasize this fact that the solution is real number.